So now with this idea of the Huckel rule, that aromatic compounds are more than just benzene, we've now got this definition of planar conjugated and 4n plus 2 pi electrons. This means that while benzene is the compound that we've referred to as aromatic all year, aromaticity is not limited to benzene. And so we can now start to look at different kinds of systems with different numbers of electrons and see how they fit these rules. And so, of course, we can start with a fairly small number of electrons, which would be 4. And the simplest compound we can have with 4 pi electrons would be cyclobutadiene. And it turned out this compound was so difficult to synthesize because it's not that stable. It wasn't until 1965 that someone was able to actually make this compound. And when they did finally make it, it had no aromatic properties. And in fact, was highly reactive and very quickly underwent a reaction where two of them combined to form this compound. So again, 4 pi electrons, that's one of our anti-aromatic numbers. There's no delocalization, and it behaves just like it's a regular alkene. So when we move up to 6 electrons, this is of course the number we've seen previously. That's where benzene falls in. But we're not limited to benzene. We can have other types of systems that are also aromatic. And that's in part because aromaticity is not limited to carbon. We can have aromaticity that involves other atoms as well. So if you replace, and we've actually seen this compound previously in the course, if you replace one of the carbons on benzene with a nitrogen, that's pyridine. Pyridine also has 6 pi electrons in exactly the same way that benzene does. And so pyridine is also aromatic. Now, so that's one way that an atom such as nitrogen can contribute to an aromatic system. Um, and that's just the same way carbon does. The 2 electrons of the pi bond, in this case the carbon-nitrogen pi bond, are part of the delocalized system. But when it comes to atoms like nitrogen as well as oxygen and even sulfur, they can also contribute in a different way. So here's a 5-membered ring, which at least initially we might think is not going to be aromatic because there's only the 2 pi bonds. But that nitrogen has a lone pair on it. And if that lone pair is able to go into a p orbital, so in other words, the nitrogen becomes sp2 hybridized, the lone pair goes into the p orbital. At that point, we do still end up with a total of a 6 pi electron system. And again, that's 4 from the 2 pi bonds and 2 from the lone pair. And that total of 6 electrons means that it can be aromatic as well. So again, when we're dealing with atoms like nitrogen or oxygen or sulfur, they can contribute in the same way that we've seen for benzene through the pi bond, or they can contribute both electrons from a lone pair. But never both. And that's because the aromatic system has to be planar, and you can't have two p orbitals that are in the same plane. P orbitals are all orthogonal or 90 degrees to each other. So these atoms, such as nitrogen and oxygen and sulfur, they can contribute in one way or the other way, but never both at the same time. And so a great example of that is the imidazole ring. So the imidazole, you can see, has two nitrogens here. This first nitrogen is contributing, through its pi bond. We also have the pi bond here, but our other nitrogen is contributing its two electrons from the lone pair. And so we have actually both types of nitrogens within this imidazole ring. Imidazole rings can be very important, especially this example. And that's the one contained in the amino acid histidine. Now, this idea of aromaticity also leads to some other interesting properties. This compound here, cyclopentadiene, we wouldn't think of this proton here as being highly acidic. But it turns out it has a pKa of about 18. And if you think about where that lets it fall, 18 is about the same range as an alcohol. And normally protons on carbon are nowhere near that acidic. So why is that one so acidic? Well, if you deprotonate it, you get the following anion. And if you think about that lone pair now that's on carbon, that lone pair on carbon is behaving a lot like that lone pair did with Perol. And so if that anion just goes into a p orbital as opposed to being in a hybrid orbital, we now have a planar conjugated 6 pi electron system. So the anion here is aromatic, which again we know is stabilizing. And so because of that, we have this unusual situation where a proton that we wouldn't normally expect to be acidic actually is. All right, let's go up some more. How about 8 pi electrons? Now, 8 pi electrons, again, that's a number that we don't expect to be aromatic. And all of the evidence agrees with that. And when you make this compound, cyclooctatetraene, and you can measure these, you find that you have, again, distinct bond lengths for the single and double bonds. And so that tells you that you have individual, isolated, single, and double bonds. There's no delocalization. Another way that you can tell is that this compound, reacts with things like bromine or aqueous acid or KMNO4 or any number of different things that alkenes normally react with. And so because it reacts under those conditions, then again, we know it's not an aromatic compound. So from this point, chemist named Sonheimer synthesized a large number of these different compounds to test the Huckel rule. And they went all the way up to about 30 carbons. And for the most part, they found exactly what they expected. So anti-aromatic, 12, 16, 20, 24, 28. Aromatic, 14, 18, 22, 26, and 30. But you'll notice we're missing something here. What about 10? So 10 carbons was not found to be aromatic. And that seemed, at least initially, to go against the Huckel rule. But it was quickly determined that when you try and make this conjugated 10-membered ring, that these two hydrogens that I've drawn in red have a steric clash. And so because of that, it can't be planar. And we know that one of the rules for aromaticity is not just the number of electrons, but that the ring has to be planar. And so turned out no issues with the Huckel rule. We've got this steric clash of these two hydrogens, and that prevents planarity. All right, so not only does aromaticity apply to all of these systems we've talked about, but it can also apply to polycyclic structures. So a compound like this, naphthalene, we count a total of 5 pi bonds, so 10 pi electrons. And so it's not just the ring on the left with the 6 electrons that's aromatic, but it's the entire ring system that's aromatic. Same thing here with anthracene. Anthracene has a total of 14 pi electrons across the 3 rings. And again, that's going to make it aromatic. We also see this applying with rings, polycyclic rings that contain other atoms. And a couple of the more important examples are both 10 electron systems On the left we have quinoline, and on the right, indole. Indoles being important most often as part of the amino acid tryptophan. And one of the more important uses of quinoline in this compound. Quinine used to treat malaria. All right, so the final thing we want to say here before we get into reactions of aromatic compounds is to go back to something we brought up a long time ago. And that's, if you recall, when we talked about proton NMR, we said that aromatic rings were unusual. They didn't really fit the patterns of other functional groups in terms of where their chemical shift shows up. Well, it turns out that it's based on this delocalization of electrons that gives us that explanation. So when you apply a magnetic field to an aromatic compound, those delocalized electrons are able to respond to that by creating a secondary magnetic field. And that secondary field is above and below the plane of the ring. And so the result is that above and below the plane of the ring, we have very, very high electron density. But the substituents on the aromatic ring, are in the plane. And so in the plane, we have unusually low electron density, and that's what leads to the very, very high chemical shifts that we see for aromatic protons.